In this video, we're going to discuss how to find domain and range from a graph. So first, we're going to start with finding the domain of a relation from a graph. So the first thing is put a box around the graph if possible. Sometimes that's not possible, but if it is, it really helps us to visualize where the domain would be. And then we're going to scan the graph from left to right, paying careful attention to the x-coordinates. So you know that the domain has to deal with the x-coordinates, and the x-axis runs from left to right. So we're scanning the graph from left to right. Number 3, consider what would happen to the graph if the coordinate grid were extended infinitely. So if I were to take that coordinate grid and stretch it out infinitely, consider the pattern, what would happen with the graph. And step 4, write the domain in set builder notation. So we have 3 examples here. We have a graph that starts with an arrow and ends with an arrow. So a graph that continues forever in both directions. It looks like this. So if I think about this graph, I notice that if I were to scan the graph from left to right, it's going to touch every single point on the x-axis. And if I were to continue this graph out, it would continue touching all of these points, and it would continue touching all of these points in this direction. So what I kind of like to think about is taking that graph and squishing it down to the x-axis, and then thinking about which places along the x-axis would that graph touch. So for this one, this is the domain x when x exists in all of the real numbers, meaning that the domain of this graph is all real numbers. This graph is going to touch every single point along the x-axis. All right, example 2. This graph starts with a point and ends with an arrow. So we have a point here and an arrow here. I know these photocopies aren't the best, so hopefully you can kind of see them well enough. So I notice I can kind of start to put a box around this graph. I can't do it in every single direction, but I could do it here. This graph has a minimum, and my minimum is going to be at x equals -1. So if I scan from left to right, I've got a minimum at x equals -1, and then my graph is going to touch the x-axis in all the points that are greater than -1. So my domain is x when x is greater than or equal to -1. So again, this is saying my domain is all x values that are bigger than -1. All right, third example, this says it starts with an arrow and it ends with a point. So this graph has an arrow here and an open point here. So again, I can't put a true box around this graph, but I can kind of find, in this case, an upper bound. So this graph has a maximum. And if I think about this graph touching the x-axis, it's going to touch in all the places where x is less than 2. So if I were to squish this down onto the x-axis, it would not touch here, but it touches all the places where x is less than 2. Since this is an open circle, my domain would be x when x is less than 2. So again, it's touching all the places less than 2. All right, to determine the range of a graph, we put a box around the graph, again, if possible. Not always possible, but sometimes, like we saw up here, we can find minimums and maximums. And then we scan the graph from top to bottom, paying careful attention to the y-coordinates. Remember, the range has to deal with the y-coordinates, and the y-axis runs vertically up and down. Step 3, consider what would happen to the graph if the coordinate grid were extended infinitely. So what would the pattern be if I took this grid and spread it out? And then write the range in set builder notation. All right, so example 1 here, we have a graph that starts with an arrow and ends with an arrow. So again, the same line. And we're going to scan that graph from top to bottom. So we're going vertically this time. So instead of squishing my graph down onto the x-axis, we're going to kind of squish it in to the y-axis. So if I take this graph, I can notice that if I were to squish it into the y-axis, it's going to touch every single point along the y-axis. Okay, so this one, the range would be y when y exists in all real numbers. All right, example 2 starts with a point and ends with an arrow. So we have a point here, and we have an arrow going up in this direction. And this graph has a minimum. The minimum for this graph is at -3. And if I were to squish this graph into the y-axis, it's going to touch all of the points where y is greater than or equal to -3. And it's equal to right here. Now notice this is a little weird because it stops here. However, if I were to continue this graph on the left-hand side, it would continue to grow larger and larger. So it is eventually going to touch all the y y-axis at all points greater than or equal to -3. So my domain would be y when y is greater than or equal to -3. Right? So this one right here, this one says starts with an arrow and ends with a point. So I've got a point up here, and I've got actually arrows in both directions this time, which is a little interesting. This graph has a maximum up here at the top. So if I think about this and I'm thinking about squishing it down onto the y-axis, I notice that this graph, if I were to squish it in, is going to touch all the places along the y-axis that are less than or equal to 3. Again, you have to think about what would happen if I were to continue that graph out infinitely in both directions. All right, to determine if a relation is a function, we use the vertical line test. If the vertical line test touches the graph in more than one location, the relation is not a function. So really quickly, just to give you an example, if I have a graph that looks like this, right, and I were to draw a vertical line anywhere along the graph, if it touches in more than one place, like this right there touches in 2 places, this would be not a function. You would have repeated x values. At this point, your x values would be the same. If you have a graph that looks something like this, it doesn't matter where I draw that vertical line, it's only ever going to touch the graph in one place. So this would be a function. All right, let's look at a couple more examples. So on this side, example 1, it says find the domain of each function. So if I'm looking at this first one, I have a line here, and if I kind of think about squishing it down onto the x-axis, I notice it's going to touch every place along the x-axis. So my domain would be x when x exists in all the real numbers. Okay. This example, again, I'm thinking about squishing in this onto the x-axis. And this one's really important to consider what would happen if I continued this pattern out. So notice this line is going to continue to get larger and larger in the x direction, and this line is going to continue to get more and more negative in the x direction. It happens quickly, but if I continue this out far enough, it will touch all the places along the x-axis. So this one is also all real numbers. All right, if I take a look at this graph here, I notice I have a point and then an arrow continuing out to the right. So my graph has a minimum, so I can kind of put that box around it, so at least block it off a little. And I'm thinking about squishing this down onto the x-axis, and then I think about what happens. The x-axis would continue to get bigger. So this is going to be x when x is greater than or equal to, and my minimum bound is 1. Okay. All right, this one right here, kind of similar. I have a point and I have an arrow going in the opposite direction. So if I think about kind of boxing this off and then thinking about where on the x-axis is it going to touch, it's going to touch at all the points that are less than or equal to -1. All right, next step, we're going to look at finding just the range. So we're looking at the y-axis this time. So my first example, I have this line here, and instead of squishing it onto the x-axis, we're going to squish it onto the y-axis. So if I think about where is this graph going to touch the y-axis, and then what would happen if I continue this out, I notice that my range is y when y exists in all the real numbers. It's all real numbers. If I were to continue this out, it would continue to touch points in this direction and then touch points in this direction. The next example has a maximum here at the top. So then I'm looking at squishing this onto the y-axis, and I notice that if I were to continue this out, it would touch all places below the maximum. So my range, y when y is less than or equal to 1, 2, 3, 4. All right, next example, I have this little curvy shape right here. I have a point, and then this continues up in this direction forever. So I notice that my graph has a minimum. And if I think about squishing it all along the y-axis, it's going to end up touching all the points that are bigger than -2, 3, 4. So my range would be y when y is greater than or equal to -4. Right, last example for range, again my graph has a minimum right here. And then if I think about squishing it along to the y-axis, I notice it's going to touch all the points above that minimum. Trace that for you so you can see it a little better. So my range would be y when y is greater than or equal to 0. Okay. Next two are finding the domain and the range. So we have an open dot here and a line. So if I'm thinking about domain, I'm thinking about squishing this onto the x-axis. So my domain is going to be x when x is greater than or equal, just greater than, it's an open circle, negative, I believe that's -2. I'm going to go with -2. A little hard to see, but thinking it's -2. My range, I have a minimum. I'm thinking about squishing this onto the y-axis. So my range is going to be y when y is greater than -3. All right, next example. This one's kind of interesting because we can actually box in this whole graph. It has two endpoints, so we can draw a box around the whole thing. My domain, again, I'm looking at my x-axis, so I can find my minimum here and my maximum here. So my domain is going to be sandwiched between the minimum and the maximum. The minimum is 0, so 0 is less than or equal to x. I do believe those are closed dots. We're going to go with closed dots. And my maximum is 3. So x is sandwiched between 0 and 3. My range is also sandwiched. I have a minimum value down here at -2. So -2 is my minimum, and my max is going to be, I think that's a -1. And my maximum is going to be at 2, and my y is sandwiched between those two values. So -1 and 2. Again, you're thinking about where is my graph going to touch along the y-axis for range. All right, last examples, we're going to determine if each function is a relation, or if each relation is a function or not. And if it is, we're going to find the domain and range. So I'm going to do my vertical line test. And if I draw vertical lines on this first graph, I notice that no matter where I draw my vertical lines, they only touch in one place. So this one is going to be a function. It's a line that continues infinitely in both directions. So my domain is going to be all real numbers, and my range is also going to be all real numbers. All right, next example. Again, if I draw my vertical lines, they only ever touch in one place. If I think about my domain, where is this graph going to touch the x-axis? If I were to squish it down, it's going to touch all the x values. So it's a function. The domain is all real numbers. And if you think about the range is a minimum, so it's only going to touch the y-axis above the minimum. The minimum is at -1, so my range would be y when y is greater than or equal to -1. My last example, if I draw vertical lines, I notice they touch in more than one place. So this one is not a function. And that completes our notes for today.